Hello friends, welcome to engineering tutorial. So we'll continue our discussion related to capacitance and capacitive circuits. So in this video we'll be discussing about the AC analysis of capacitive circuits. So first we'll be discussing about purely capacitive circuits, that is circuits involving only capacitor, and then resistor and capacitor, the RC circuit, okay, the AC analysis. So here we have a purely capacitive circuit consisting of a capacitor, an alternating EMF for voltage ET, which produces a time varying current IT. So how it happens? First we have the alternating voltage, which is expressed as ET is equal to E0 sine omega t. E0 is the amplitude, omega is the angular frequency, t is the instantaneous time. Now we know that for a capacitor, Q, that is the charge, is directly proportional to the voltage, in this case the time varying EMF, or Q is equal to C E T. So ET is equal to Q by C. Now we know the current through the capacitor is the rate of differentiation of the time varying charge, so it is dQ by dt. So that gives us the differentiation of this CET. Capacitance is the proportionality constant, so it goes outside. D by dt of E0 sine omega t, that gives us omega E0 cos omega t combined with the proportionality constant, which is the capacitance. So it can be rewritten as E0 by 1 by omega c sine omega t plus pi by 2. Cos omega t can be written as sine omega t plus pi by 2. Now if you compare here this current expression, where it is expressed as this I0, the maximum value of the current, that is equal to E0 by 1 by omega c. If you compare this expression and this expression, which is the time varying EMF, you will see that the current is leading the EMF, okay, the current is leading the EMF by a factor of pi by 2 radian or 90 degree. So current leads voltage, sorry, it is E, not V, E, same thing, but we have expressed it as E, so it's better to stick to that. So current leads the voltage or time varying EMF by pi by 2 radian or 90 degree. Okay, so if we want to express it in the form of two waveforms, here we have the blue one, which expresses the alternating EMF, okay, where this is the amplitude E0, and the red one represents the time varying current, resultant current, with the maximum value, how much? I0, this. And if you see, the current is leading the voltage by pi by 2 radian, this much factor, pi by 2 radian or 90 degree. So in terms of phasor diagrams, we have this here, the current. It can be anything, mostly it is represented in terms of the RMS value or virtual value, okay. So you can say that this is the virtual value or the RMS value, okay, blue, okay, this is in blue, so the RMS value or the virtual value. So here if you see also, the current is leading the voltage by 90 degree, or you can say the voltage or the EMF is lagging the current by 90 degree. Current is leading the EMF by 90 degree, or the EMF is lagging the current by 90 degree. So here this factor, okay, 1 by omega c, that is very important, this factor, okay, this 1 by omega c, that is very important. So this 1 by omega c is what is called as the capacitive reactance. reactance. So the capacitive reactance of a capacitor C is the opposition provided by the capacitor to current flow. It is expressed as XC, X subscript C, where X is the symbol for reactance, and here it is because of capacitor, so it is capacitive reactance. Same goes for inductance. There is inductive reactance. As inductor and capacitor, they are frequency dependent circuit elements. Resistor is frequency independent. There is no omega thing involved with resistor. For inductors there is, for capacitors there is. We'll be discussing about inductors. So Xc is the capacitive reactance, 1 by omega C, which is the opposition provided by the capacitor to current flow. It has the same units as resistance, which is ohm. Okay, then in terms of complex representation, capacitive reactance using complex notation can be expressed as Xc, capacitive reactance, is equal to 1 by j omega C, which is equal to minus j by omega C, multiplying j in both the denominator and the numerator to rationalize it. It becomes minus j by omega C. So in terms of complex analysis also, if you try to understand it, the voltage drop across the capacitor will be, it will be in terms of the RMS value or the average value, IV into minus j by omega C, which is the capacitive reactance. This is equal to minus j IV by omega C, minus j. Okay, this is what the voltage drop across the capacitor, which is the same as the EMF. Okay, Vc, which is equal to ET for the purely capacitive circuit. So that's why in terms of phasor analysis, this also equal to the voltage drop across the capacitor. Okay, this is the negative imaginary axis. This is the real axis. This is the negative imaginary axis. This is the positive real axis. So the voltage drop across the capacitor, it is expressed as minus j into IV by omega C. Minus j means the negative imaginary axis and the current with the reference phasor in the positive real axis. So obviously the EMF or the voltage drop across the capacitor, it is lagging behind the current by 90 degree. Okay, so then we have the instantaneous and average power. So the instantaneous power in a purely capacitive circuit is represented by the product of the time varying EMF and the time varying current, which is expressed as this. Okay, the product of these two values, Et into It, E0 sin omega t into E0 by omega c sin omega t plus pi by 2, or I0 if you can express it in any form. So that when we do the trigonometric simplification, it becomes E0 I0 by 2 sin 2 omega t. Okay, I'm not going into the detailed derivation directly, the direct results I'm showing, and the average power for a purely capacitive circuit, that is equal to 0. Okay, then we have is the AC analysis of circuit containing both R and C in series. Okay, so now let us deal each of them separately. First, if you try to recall, in AC analysis of purely resistive circuits, we studied that the voltage drop across the resistor, or the voltage across the resistor, and the current, they are in the same phase. There is no phase difference for purely resistive circuits. There is no phase difference. Okay, phi is 0 radian or 0 degree, both the same thing. Okay, for purely resistive circuit, no phase difference. For purely capacitive circuits, the voltage across the capacitor, the voltage drop across the capacitor, that lags behind the current by 90 degree. Okay, for purely resistive, 0 degree. For purely capacitive circuit, the phase difference is minus pi by 2 radian or 90 degree. So it's common sense that for RC circuit, that is circuit involving R and C, the phase difference will neither be 0 degree or 0 radian or 90 degree, that is minus 90. It will be somewhere in between. Okay, somewhere in between 0 degree and minus 90 degree, somewhere in between here, like this. So for a AC circuit containing both resistor and capacitor, the phase difference is phi somewhere in between a purely resistive circuit, that is 0 degree or 0 radian, and a purely capacitive circuit with 90 degree or pi by 2 radian. Okay, negatively. So it is somewhere like this. Okay, where current is the reference phasor, the voltage drop across the resistor, that is in phase with the current, and the voltage drop across the capacitor, that is lagging behind the current by 90 degree, minus pi by 2 radian or minus 90 degree, and the resultant voltage, which is the combined result of these two voltage phases, that is this, which is lagging behind the current by minus phi radian or that much equivalent degree. So it is in between a purely resistive circuit and a purely capacitive circuit, somewhere in between. And in waveform form, it is like this. Okay, so here the phase difference is phi radian. Okay, and here some concepts. The result is the square root of the VR square and VC square, that is the squares of the individual voltage drops, that is the voltage drops across the resistor and capacitor. Okay, and this is what is called as the voltage triangle. Okay, where the voltage and current phases that are represented, that is called as the voltage triangle. And if we divide it with the current, okay, if we divide it with current respectively, it becomes the impedance triangle. Okay, impedance triangle, dividing all the voltages with the respective RMS or virtual value of current. VR by IV, EV by IV, and VC by IV. That will give us the resistance, the capacitive reactance, negative of course, and this is the resultant of the resistance and capacitive reactance, that is Z is equal to R square plus XC square. This is called as the impedance, the net impedance, the combined result of both the resistance and the capacitive reactance. Okay, and then we have the phase angle, the margin by which the net EMF or the net impedance is lagging behind the current, the reference phasor, that can be expressed in terms of the impedance values, that is the capacitive reactance and resistance minus XC by R, or if we follow the voltage triangle, that will be equal to tan phi is equal to minus VC by VR. So phi will be equal to tan inverse of minus Vc by Vr. So here it will be phi will be equal to tan inverse of minus Xc by R. So whichever way you want to go, it will be the same thing. The same result you will be getting. Okay. So this is the voltage triangle. If we divide it by the current, we will get the impedance triangle. So these are some of the basic concepts related to AC analysis of circuit containing both capacitor and resistor. And these are the EMF and current, time varying EMF and time varying current expressions. Same E0 sin omega t, and the current here same E0 by 1 by omega c, where 1 by omega c is the capacitive reactance, okay, capacitive reactance, and this E0 by 1 by omega c, that is the maximum value of the current. And here the phase angle difference is phi, which is greater than 0 degree, okay, greater than 0 degree but lesser than 90 degree, minus 90 degree, like in between 0 and 90 degree, okay. And these are some of the concepts, okay.